In this video, we are going to graph conic sections with polar coordinates. So we're going to start off with our forms of polar equations. So we have r is equal to EP over 1 minus e cosine theta as our first one. And this involves a definition with the focus and also eccentricity. So your focus, we've had focuses, or we had foci in other conic sections like your hyperbola and your parabola, but here your special case is that for all of these conic sections in polar coordinates, your pole is going to equal to your focus. And if you have multiple foci, then at least one focus is at the pole. So your E is also equal to your ratio of C over A, and this is your eccentricity, aka your measure of how circular your conic function is. An eccentricity of less than 1 is going to be an ellipse. An eccentricity equal to 1 is going to be a parabola, and a eccentricity that is greater than 1, that is going to be a hyperbola. And your orientation rules you have to remember is cosine theta is going to mean you have a horizontal axis, and a sine theta means you have a vertical axis. Now let's talk about our directrix direction. So everything is going to boil down to where you can figure out where the directrix is going to be. So in r is equal to EP over 1 minus cosine theta, you're going to have a directrix to the left. And it's p units from pole. Now, your directrix is going to be perpendicular to the polar axis. So in this column, we're going to have connection to polar axis. It's going to be perpendicular to it. Now, for our next form, we have r is equal to EP 1 plus e cosine theta, and this is going to have a directrix that is to the right, p units from the pole, and it's going to have a perpendicular connection to the polar axis. So the directrix is perpendicular to the polar axis. Now for r is equal to EP 1 e minus sine theta, your directrix is going to be below, and it is going to be p units from the pole. P units below the pole, and it is going to be parallel to the polar axis. Now for r is equal to EP 1 plus e sine of theta, it is going to be above, so it's going to be p units above the pole, p units above the pole, and it is also going to be parallel. So what you can see here is the main thing you're looking at is going to be what this denominator is. So when you have cosine theta, it is always left and right, and when you have sine theta, it's up and down, as we can see here. So you see that cosine theta, left and right, and sine theta, we see below and above. Now, For an ellipse, the directrix is going to be perpendicular to a major axis. So for an ellipse, your directrix is perpendicular to major axis. And for a hyperbola, the directrix is perpendicular to transverse axis. Now, let's do some practice problems. So, let's say that we have a question that is going to be r is equal to 6 over 1 minus 1 over 3 cosine of theta. So what you have to do is convert it into your standard form. And the standard form is r is equal to EP over 1 minus e cosine of theta. Now, comparing this with our version, we can identify e is 1 over 3 and EP is equal to 6 simply by looking here. And e is 1 over 3 because that is that coefficient out in front. So if you solve for p, we know that p is in this situation, right? So p is equal to 6 over 1 over 3 because we know that 1 over 3 was here and 6 was our value above there. So now that is going to equal to 6 times 3 over 1, and that's equal to 18. So when you have an eccentricity that is less than 1, here, eccentricity is less than 1, that means that you have an ellipse. Now, we have to look at where will our directrix be. So looking at this equation, we see we have a minus here. A minus means that the directrix is left of the pole and is perpendicular to your polar axis. Now, let's also find what our polar axis intercepts are. So you're going to plug in some angles that are easy, like theta is equal to 0, which would give us r is equal to 6, 1 minus e, which is 1 over 3 cosine of 0. Cosine of 0 is equal to 1, and that's 6 over 1 minus 1 over 3, aka 1 over 3. You can write that as 4 over 4. That would give you 1 over 3, or that would give you 4 over 4. That would give you, and then you have to convert that into a common thing. So you would have 6, 4 over 3. Instead of 3 over 3, you could just make this equal to 3 over 3, actually. And then you would have 3 over 3 minus 1 over 3. But this is actually a plus. So this is a plus, so that's why you get 4 over 3. So this is 9 over 2. So your point is going to be 9 over 2 pi. Now, after this, how do you graph this? You need to graph the pole, which is going to be the focus at the origin. Now, you need to graph your directrix. So let's break up this into a different... So we'll make that negative 18. And we're going to plot the polar intercepts. And one of them is going to be at 9 over 2 pi. And then we have one that is at 9, 0. Because we got this 9, 0 point from looking here. So this is where we got, this is actually theta is equal to pi. And theta is equal to 0 is r is equal to 6 over 1 plus, or 1 minus, 1 over 3. That is equal to 6, 2 over 3, and that's equal to 9. So that's where you get the point 9, 0. Now, let's graph these points. So if we make, let's see here. Let's just make this in intervals of 3, so let's keep that actually. Let's make that negative 18, and we make that negative 6, and make this negative 12. So where would 9, 0 be? 9, 0 would be around here. I mean here. And then 9 over 2 pi. So that's 4.5. 4.5 would be around here, and then up 3.14. That would be somewhere here. So 9 over 2 pi. So because e is greater than 1, we're going to draw a closed ellipse that is symmetric about the polar axis. Now, how would this look like? Let's also consider the points. So give me 1 second, or so you're going to have a graph that looks something like this. So it passes through 9, 0, and it also passes through approximately here. So that's going to be 9 as well. So somewhere over here, a little bit past here, and we're going to have our ellipse. And it's going to be symmetric about the polar axis, which is this. So let's do our next question.